Video lecture of this course. We want to look at the applications of singular value decomposition. So, applications of singular value decomposition. The first one is image processing, which can also be extended to machine learning. Suppose you want to send a picture with 1000 by 1000 pixels. So instead of sending an image of 1000 by 1000 pixels, which is 1 million, we send the essential information. And what is the essential information? And the essential information is the key is the singular values. Key is the singular values. And what is the key there? So some are significant. Some are significant, and others are extremely small. Extremely small. That's why we order them when we enter them, or when we write them in the sigma matrix. Extremely small. So if we keep 20 and throw away 980, then we send corresponding 20 columns of U and V. And how is that? Because A equals U sigma V transpose, which we just saw from the spectral decomposition theorem, is U1 V1 transpose plus sigma 2 U2 V2 transpose plus sigma R UR VR transpose. And these are all matrices of rank 1. So these are, so A is a sum of R matrices of rank 1. So if only 20 terms are kept, so if only 20 terms are kept, then we send 20 times 2000. Why 2000? 1000 for U and 1000 for V. 2000 numbers, and these are probably the vectors. 1000 and 2000 numbers instead of this 1 million. Instead of 1 million, this implies a 25 to 1, because this is 40,000. 1 million is a 25 to 1 compression. So you save on information that you are sending if you send it like this. Okay. So what we are actually saying is we can always put a threshold. We can always put a threshold, and all sigmas that are below that threshold, we don't need to send that information. And the information that is left is actually sent to this relationship, and this will give us a savings of information, savings of in information that we are actually, it's not saving of information, it's saving of the capacity that we are transmitting. Second is the effective rank. How do you compute the effective rank of the matrix? So first one was image processing, and then we have effective rank. So we know the rank is the number of independent rows or columns, and this is also the number of pivots, right? So rank is the number of independent rows or columns, so it's the number of pivots. So for example, if when I'm doing some numerical calculation, these are the matrices I get. So here we have probably 2 pivots and rank is 2. Here we have 1 small pivot, and here we have rank is 1, and round of error and round of error produces a second pivot, right? However, the effective rank of all these matrices, so the effective rank is 1 when epsilon is less than 10 minus 6. So why is that? Because we can use A transpose A or A transpose. They have the same rank as A, have the same rank as A. We can use A transpose or A transpose and find eigenvalues, find their eigenvalues, which are actually the singular values, implying singular values of A, and if we fix a threshold, and count singular values, above the threshold, this will give us the effective rank. And if you recall, the number of singular values is up to R, where R is the rank. So if we threshold the singular values, and singular values are listed in order of decreasing magnitude or decreasing amplitude, magnitude is fine. So this will give us the effective rank. Okay. The third one is the polar decomposition. We already know we can write a matrix in terms of A equals LU. We can write a matrix in terms of A equals QR. And now there's another, and we also know we can write a matrix in terms of M inverse. What is that? M inverse AM or MA inverse? M. So A M B is M inverse AM. So we can write this as M inverse, right? So I can write a matrix in terms of, or I can, in general, I can write in terms of the Jordan form too, or this is M, maybe I write it in terms of the Jordan form, Now we also have one more, which is we can write any real square matrix in terms of an orthogonal matrix and a symmetric matrix. So how do we do that? So this concept is taken from the complex number. So recall, if Z is a complex number, V is a complex number, then Z is equal to R, E, J, theta. R is positive. So in terms of matrices, we'll say this is a positive definite matrix. Okay. And Ej theta is an orthogonal matrix. In terms of matrices, this is an orthogonal matrix. Okay. Why? Because Ej theta into E minus J theta is 1, forms a 1 by 1 unitary matrix. UH into U equals I. So we can extend SVD. So SVD extends this polar factorization. This is the polar form of the complex number. This is the polar form. One is the polar form, the other is the rectangular form. So SVD extends this polar factorization. To matrices of any size. So every real square matrix, can be factored into, A equals QS, where Q is orthogonal and S is symmetric positive semi-definite. Symmetric positive semi-definite. If this positive semi-definite becomes positive definite, so if this so when this becomes positive definite, then A inverse exists. So the inverse exists if this becomes positive definite. So let's see how do we do that. So A equals U sigma V transpose, and in here I'll insert an identity. So we'll say V transpose V. So V transpose V is I, and this is sigma V transpose. So since matrix multiplication is associative, I'll put a parenthesis over here, and I say this is equal to Q into V sigma V transpose, or maybe I say this is equal to Q into S, where this is Q. So since U and V are both unitary matrices, so unitary or orthogonal, So the product is also orthogonal or unity. So product of orthogonal, orthogonal or unitary matrices is orthogonal or unitary or unitary, or maybe this is not, is also orthogonal or unity. So these are two orthogonal matrices. So Q is orthogonal, and V sigma V transpose. If I take the transpose of this one, this is again the order is reversed. So this is V sigma transpose V. But since this A is square, the sigma is diagonal. So we still have V sigma V transpose, because A is square. A is square. So which is, and this is equal to S, which is symmetric. Okay, so if this is square and positive definite, then obviously there is sigma. Sigma doesn't have any zeros, so obviously this is invertible. Okay, and or A is equal to QS, or A equals QS, and A transpose A equals QS transpose into QS, which is equal to S transpose into Q transpose into Q into S, but this is I because it's orthogonal, and this is equal to S is symmetric. This is symmetric. If this is symmetric, this means S transpose equals S, so this is simply S squared. So A transpose A is simply S square. So, and this is this matrix is, when this matrix is this is already symmetric. This is always symmetric. So always symmetric. And if it is positive definite, if this is positive definite, then this implies A inverse exists. A inverse exists, or A which is equal to QS implies Q equals, so I multiply an A inverse here, I multiply an A inverse here. So I'm sorry, I multiply an A inverse here, or A is equal to Q. So A inverse exists. A inverse exists, or maybe S inverse. So S inverse exists. S inverse exists, and or if I'm, or since we have A is equal to QS, if I multiply S inverse over here, I multiply S inverse over here, S inverse over here. So Q equals A times S inverse. Okay. And this is only possible when this matrix is positive definite. And when this is positive, this definite, this also implies A is non-singular. A is non-singular because A has independent columns. This we saw in chapter 3, by the way. For complex matrices, Q is unitary, and S is Hermitian. Rest everything else is true. So let me give you two examples, and you should go back home and see whether you can come up with these solutions or not. So let's say A is 1 minus 2, 3 minus 1, and my claim is this is equal to 0, minus 1, 1, 0. This is obviously orthogonal. This is Q, and then I have 3, minus 1, minus 1, 2. Obviously this is symmetric because the off diagonal elements are the same. So go home and see whether you can derive this relationship or not. We can also write, instead of A transpose A, I can do A transpose, and then I can come up with another form so let's see whether you can come up with this one or not. So let's see, A is equal to S prime Q, and A is 1 minus 2, same matrix, 3 minus 1, and S prime is again a symmetric matrix. This is S prime, and this one is Q. So go home and see whether you can decompose this result or not. How did you come with S prime Q? That's very simple. So over here, instead of doing V transpose V over here, I think you do you make this you insert over here, somewhere over here. So let's see if we can do that. So how did we get this one? So recall, A is U sigma V transpose. So we inserted a V transpose here. Let's insert a U transpose U over here. If you do that instead of this one, if you do that, so this becomes U sigma U transpose and U times V transpose, right? This is still symmetric, so let's call this S prime. This is still orthogonal, so let's call this Q. So this is how we get this one. Okay. So where do we have this application of polar decomposition? So A equals SQ, or A equals QS. A equals QS probably, or SQ. Well, both are the same actually. Both are derived from the singularity decomposition. Finds use in robotics. It finds use in robotics, where we want to separate. If you want to separate stretching from rotation, if we want to separate stretching from rotation. So orthogonal matrix is rotate, if you recall from chapter 2, from rotation, then QS achieves that. QS achieves that, meaning Q is rotation or reflection. And S has eigenvalues that stretch or compress. And this is how you separate both the actions. Okay. And then the fourth application, this is the third or the fourth. So the fourth application, which is the most important one probably, the fourth application, which is the most important one, is the least squares. So recall from chapter 3, in a rectangular system, AX equals to B has a solution. When we have that normal equations, has a solution. If we multiply A transpose here, I multiply A transpose here, then we get a set of normal solution. As normal solution, A transpose A, X equals A transpose B, I think you put a X hat on top of it, right? So this is a set of normal equations. If we solve them, this is the projection and so on and so forth. Chapter 3, all of chapter 3. So chapter 3. So if A has dependent columns, so if A has, maybe this one, yes. So if A has dependent columns, then A transpose A inverse does not exist. Does not exist. If it does not exist, then obviously you have to project it. Does not exist, and X hat is not unique. If the inverse was existed, then I could have multiplied the inverse here, I could have multiplied the inverse here, and that is the solution of the projection. If you recall, P times B, X hat is P times B, is not unique. So what did we do? So we chose, so what was the solution? You choose a particular solution of, a particular solution of A transpose A, X hat equals A transpose B, which is the shortest, the shortest. So this is the perpendicular, so the perpendicular error from the vector B to onto the column space of A, which is the shortest. So what is the optimal solution? So optimal solution of AX equal B is minimum length solution, that's why it's least squared, minimum length solution of A transpose A, X hat equals A transpose B, right? And this minimal length solution is called, this minimal length solution is X plus. Okay. And if A has independent columns, this implies A transpose A whole inverse exists. Okay. So if this exists, then this implies A transpose A X hat equals A transpose B has a solution X hat equals A transpose A whole inverse A transpose B, right? And obviously this we define this as A plus. This is not A transpose, this is a plus. So this is a plus sign, and we call this the pseudo inverse. PSU, I think. Pseudo inverse. Kind of an inverse, right? Okay. And let's compute and see. So let's do some examples and see what is this X hat equal to. X plus, I'm sorry. So or X hat or X plus, whatever we want to call this. So let's say A equals, this is a tall matrix, 1, 1, 1, 2, 1, 3. So let me do minus row 1 plus. So what I'm trying to do, I want to find the rank. So obviously the rank is either going to be 1 or 2, right? Because there are 2 columns, there are 3 rows. So obviously the rank is going to be the minimum of 2 and 3, which is 2. So it's either going to be 1 or 2. So minus row 1 plus row 2, minus row 1 plus row 3 what do I get? 1, 1. Minus 1 plus 1 is 0. Minus 1 plus 2 is 1. Minus 1 plus 1 is 0. Minus 1 plus 3 is 2. And then I say minus 2 row 2 plus row 3. If I do that, I have 1, 1, 0, 1, 0, 0. And then over here I say this is minus row 2 plus row 1. If I do that, this is 0. If this is 0, this means this is a pivot, this is a pivot. This implies rank equals 2. So it implies 2 independent columns. Okay. So if you have 2 independent columns, then obviously, so both the columns here are independent. So this implies A transpose A inverse exists. So since this inverse exists, let's calculate this one. So what is A transpose A? So this is not A plus. So A transpose A is equal to A transpose, this is A transpose A. So A transpose A equals, so A transpose is 1, 1, 1, 2, 1, 3 multiplied by 1, 1, 1, 1, 2, 3. So it's going to be a 2 by 3, 3 by 2. So obviously I'm going to have a 2 by 2 matrix, and that 2 by 2 matrix is, so when we have 1, 1, 1, this means I simply add all the elements in the column. So 1 plus 1 plus 1, 3, 3, 4, 5, 6, and 1, 2, 3 means 1, 2. So first row is multiplied by 1, second row is multiplied by 2, third row is multiplied by 3. So 1, 3, 2, 6. So it's already symmetric, but no need to calculate this one. Then this is simply the length. So 9 plus 1, 10 plus 4, 14. Okay. Is it right? Okay. And A inverse equals, so the determinant here, so what is the determinant? So determinant here is 14 to 3 is 42, 42 minus 36 is 6. So this is 6, so this is 1 over 6. And for a 2 by 2 case, I swap these two. So this is 14, this is 3, and put a minus sign off diagonal elements. So it's minus 6 and minus 6. So A plus, this is plus, this is not, so A plus equals A transpose A whole inverse A transpose. So this is equal to, where is the transpose? So this is a transpose. So if I put a transpose here, so this will become 1 over 6. And this is going to be 2 by 2. And this is 2 by 3. 2 by 3. So I am going to have a 2 by 3 matrix. So 2 by 3 matrix. So this inverse, so 14 minus 6 is 8. So 8 over 6. 8 over 6. Then I have 14 minus 12. 14 minus 12 is 2, 2 over 6, which is 1 over 3. Then I have 14 minus 18. 14 minus 18 is minus 4. Okay. And then I have minus 6 plus 3. Minus 6 plus 3 is minus 3. Minus 6 plus 6, this is 0. And then I have minus 6 plus 9. Minus 6 plus 9 is plus 3. Okay. Or this is equal to, so 8 over 6 is 2, 4 over 3. 4 over 3. This is 2 over 6, which is 1 over 3. This is minus 2 over 3. This is minus 3 over 6, which is minus half. 0 is 0. 3 over 6 is half. Okay. And you can check whether this is true or not, whether this gives you the same result or not. So some properties, so properties of a pseudo inverse. So if I have A, which is m by n, and I multiply by a pseudo inverse, which is n by m, and then I multiply again by m by n, so this is equal to what? So this is equal to, so this is actually the left inverse. This is the left inverse of A, and this is equal to 8 and m by n. And similarly, if I have A pseudo inverse n by m, and then I have A, which is m by n, and then I have again A, which is m by, or maybe pseudo inverse here, n by m. So this is equal to, again, this is the left inverse, so this is identity. This is equal to A pseudo inverse n by m. So A plus and A plus A are both symmetric. Is this right? So A plus, is this right? A is m by n, this is n by m, and we are left with m by m. This is n by m, this is m by n. So obviously they are square matrices, so maybe they are symmetric. You can go check. So you can check whether this holds or not. Okay, so let's do another example. This is the projection example that we did in chapter 3, but another way to solve it. So A is a diagonal with dependent rows and columns. So A is diagonal with dependent rows and columns. So if the rows are dependent, obviously the columns are also independent, or are dependent. So let's say this P is some AX hat. So this P is the projection onto the column space, and this is equal to some sigma 1, 0, 0, 0, 0, sigma 2, 0, 0, 0, 0, 0, 0. Okay. And obviously we have 1, 2, 3, 4, so 4 unknowns. X1 hat, X2 hat, too far away, X2 hat, X3 hat, and X4 hat. Okay. And this is, let's say, equal to some B1, B2, B3. So the original B was, so original B was equal to B1, B2, B3. So what we have done is we have projected this one and we have made this one B3 equals 0. Okay. So in the column space, the closest vector to, so in the column space of A, the closest vector to B is this one, right? Is this one is P, which is equal to B1, B2, 0. So imagine you are in a three-dimensional space and your column space is the floor. So obviously the Z component is 0 and your projection is on the floor. So the best we can do is to solve the first two equations, since the third equation is 0 equals B3, right? So the error cannot be reduced. But the errors in the first two equations will be 0. In the first two equations will be 0. This implies x1 hat equals, what is x1 hat? So x1 hat multiplied by this one equals b1. So obviously x1 hat is b1 over sigma 1. Is b1 over sigma 1, and x2 hat is b2 over sigma 2, right? And how to make x hat as short as possible, and how do we make x hat as short as possible, as short as possible. You put you 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 put x3, you say x3 equals x4 equals 0, right? So what is the minimal length solution? So minimal length solution is obviously this one. So let's compute whether it's the same or not. So minimal length solution, x hat x plus is, so x plus is equal to a pseudo inverse into B. And what is a pseudo inverse? So a pseudo inverse, this is equal to, a pseudo inverse is simply 1 over sigma 1, 0, 0. So this is m by 1. This is n by 1, right? This is m by 1. This is m by 1. This should be equal to n by m. And this is n by 1. So n by m. So instead of 3 by 4, we'll have 4 by 3. So 4 by 3 is this one, this one, this one, multiplied by b1, b2, b3, which is equal to simply b1 over sigma 1, b2 over sigma 2, and finally we have 0, right? 1, 2, 3, 4. And this is our minimal length solution. This is our minimal length solution, where this is the pseudo inverse and this is B. Okay, and so recall if sigma m by n, if sigma m by n is like this, 0, 0, 0, this is sigma 1, this is sigma r. So this implies sigma plus, which is n by m, is simply 1 over sigma 1, 1 over sigma r, and then we have this matrix over here. So 0, 0, 0. Okay. And sigma plus b is simply b1 over sigma 1, br over sigma r, and then we have this 0 over here. Okay. So my claim is, so what do I claim? So my claim is, shortest solution or minimal length solution. So minimal length solution, minimal length solution x plus is always in row space, of A. Is always, this is transpose, is always in row space of A. How? So if we say x hat equals xr, the row space component, plus the null space component, this is the row space component, and this is the null space component. Null space component. So if I multiply both sides by A transpose A, so multiply both sides by A transpose A, then I have A transpose A into X hat equals A transpose A into XR plus A transpose A into X, and I can always put a 0 here, so this is equal to 0 because Xn is in null space, because Xn belongs to the null space of A. So this is simply equal to A transpose A XR. Okay. Second, and this is equal to what? This is equal to B, by the way. This is equal to A transpose B, I think so. Yeah, this is equal to A transpose B. So when I multiply A transpose A, so this is equal to A transpose B, because AX equals B. So if I multiply A transpose here, obviously it's going to be A transpose X. Okay. Also, if I find the norm square of X minimum solution, this would be, so X hat, this would be simply norm square of this one plus the norm square of this one, right? So X hat, so this implies X hat is shortest when Xn equals 0. Okay. And finally, all solutions, so Xn is equal to 0 means okay, all columns are independent, right? So Xn is equal to 0 simply means all columns are independent. So all solutions of A transpose A X hat equals A transpose B have same row space component, which is X plus, okay. And how can we show this? So let's draw the same picture. $90 here, 90 degrees here. This is the row space. This is the null space. This is Rn. This is Rm. This is the column space. This is the left null space. Okay, so we have some vector here and something here. So there is E here, the component, the orthogonal, the drop onto the this X is the drop from B onto the column space, and then I have some P here. So this P is actually A times X plus, right? Okay, so this P is A times X plus so this P is X plus, and what is this? This is B, right? This is B, which is, these are the two perpendicular. So this is B. This is, there is this X plus here, which is XR. So what happens is this P will go over here. This is a pseudo inverse into P should be equal to X plus, and then this is also going to go over here. This is a pseudo inverse B. This is X plus, and this E goes here. This E goes here. Maybe I just put it over there. And this is a pseudo inverse E. This goes in the null space. This goes in the origin actually. So this goes in the origin over here. So what I'm trying to say here is this is the origin here too. So this is the origin here too. So the pseudo inverse knocks out the left null space, by sending it to 0, and it knocks out the null space of A by choosing x plus as XR. By choosing x plus as XR. So this is basically XR. Right? So this is the row space component. So this is always of minimal length because there is no null space component with this one. Okay. So there exists an pseudo inverse n by m that always gives x plus as it takes back vector b and p in Rm back to, takes up b and p in Rm back to x plus in Rn. So if A equals U sigma V transpose, this implies pseudo inverse is V sigma plus and U transpose, or X plus is A pseudo B, which is equal to V sigma plus U transpose into B, right? So this is how you compute the least square solution of AX is equal to B. So let's do some examples. And yeah, so let's do some example. The first one is A equals 1 0 0 1 0 1 0 1 0 1 0 0 1. So this implies the rank is this pivot, the rank is 2. So if the rank is 2 and this is 2 by 3, if this is 2 by 3, this is M, this is N. So it's best for me, since this is a fat matrix, I should calculate AA transpose. So what is AA transpose? This is 1 0 1 0 0 1 into transpose 1 1 0 0 0 1. This is going to be a 2 by 2 matrix, and this 2 by 2 matrix is symmetric matrix. So I add the first and the second rows, so 1 1 2, and no contribution of the third row. Here again 0, and then here I just pick the third one, so pick the third one 0 1. So this implies lambda 1 is equal to 2 and lambda 2 is equal to 1. So if you compute A transpose A, which I'm not going to do, So if you compute, and I will encourage you to do that, if you compute A transpose A, you'll find lambda 1, because it's going to be a 3 by 3 matrix, because this is 3. So lambda 1 is going to be 2, lambda 2 is going to be 1, and lambda 3 is going to be 0, because they share A transpose A and A transpose both share the non-zero eigenvalues. They share the non-zero eigenvalues. Okay. So if this is 2, so this implies sigma 1 is under root 2 and sigma 2 is 1. So since the rank is 2, so implies two independent columns or rows, because there are two pivots, so obviously the two pivot columns and two pivot rows are independent. Okay, so what is U? So U has eigenvectors of A transpose. So if lambda 1 equals 2, so A transpose minus lambda 1 I gives me what? This gives me 2 minus 2, 0, 0, 0. So this is 0, 0, 0, and 1 minus 2 is minus 1, or which I can always do plus 1. This is my pivot, so this implies U1 is free variable is this one, and this one is 0, right? Okay, good. And for lambda 2 is equal to 1, and for lambda 2 is equal to 1, this implies A transpose minus lambda 2I equals 1, 0, 1, 0, 0, 1, sorry, 0, 0, 1, 0, 0, 0, 0. So these were eigenvalues because they are on the main diagonal. Okay, so this is a pivot, so this implies U2 equals free variable and over here. So excellent. So U is, so this implies U, which is U1, and U2 is actually an identity matrix. It's 1, 0, 0, 1. And since this is a fat matrix, I can use, if it's a fat matrix, then I can use A transpose UI. So this is fat, A is fat. This implies A transpose UI equals sigma I Vi, right? A transpose UI equals sigma I Vi for I is equal to 1 up to R, and R is 2. Okay, so let's do that. So A transpose, so I had A transpose here. So A transpose is this one, 1, 1, 0. This is 1, 1, 0, 0, 0, 1. 1, 1, 0, 0, 0, 1. 1, 1, 0, 0, 0, 1. Okay. And U1 is 1, 0, which means I'm picking the first column. 0, 1 means I pick the second column. So this implies V1 is first column, which is 1, 1, 0, and I can normalize it. And V2, no need to normalize there, this is already 1 only. V2 is I pick the second column, which is 0, 0, 1. Again, both are orthogonal, so don't need to worry. These are also orthogonal. And what about A times V3 or A times Vi is equal to 0. A times Vi equals 0 for I equals R plus 1 up to N. So N here is 3. R plus 1 is also 3, so it's only 1. And let me check, it's yes, A R1 R plus 1 to N. So what is A V3? So A times V3 is equal to 0, implies V3 is in null space of A. And where is A? A is this one. So what is the null space of A? Null space of A is, so let me write it here. So A is 1, 0, 1 0 0 1. This is a pivot, this is a pivot. So the second is a free variable, so this implies v3 equals, second is a free variable, which is this one. This one goes here, becomes a -1, negative here, and this one is 0. Again, I do 1 over root 2. Again, check. So this one is, so v1, so v1 is orthogonal to v2. So always check. So this is orthogonal, and v1 dot v3. So v1 dot v3 is -1 plus 0, so this is 0, and v2 dot v3 and v2 dot v3 is also 0. So these are all three orthogonal. So u is an identity, and v is, so this implies v is 1 over root 2, 1 over root 2, 0, and then it's 0 0 1, and finally -1 over root 2, 1 over root 2, and 0. Okay, so what is or a pseudo is, so a is u sigma v transpose. So if I take the inverse of this one, so this implies a pseudo is v sigma plus, which is just the inverse, meaning 1 over sigma I, and then u transpose. Okay, so 8 is this v, which is 1 over root 2, 1 over root 2, 0, 0, 0, 1, minus 1 over root 2, 1 over root 2, 0, v. Then sigma plus is, so this is 3 by 3. Sigma, so this is, this one was m by n. This is m by m. This is m by n. This is n by m. So this is n by m. This is n by m. This is n by m. This is m by m. So n by m. So now we have how many columns? We have 3. So 3 by 2. So 3 by 2. So my sigma plus is, so it's 2. It's 2 or under root 2. It's sigma I. Sigma I is, did I write sigma I? So let me write. So sigma I is actually, sigma 1 is under root 2 and 1. So it's under root 2 and 1. So it's 1 over under root 2, 1 over under root 2, 0, 0, 1, and then 0, 0 over here, right? And then we have I, this is I, so it doesn't make a difference. So this is I. So this is equal to then, so if I multiply this out, this is going to be equal to 3 by 2. So 3 by 2, so this is 3 by 2. So half here, 0 and half. So half here, half 0, so this is 0. Half, 0, and finally I pick the second one, which is 0 and 1. So this is my pseudo inverse, and you can see, you'll see that this is actually, this gives you the answer. Okay, let's look at another example. I am not going to solve this one using the singular value decomposition, because this is much easier if I solve it like this. So if A is 1 1 0 1 0 1, this implies rank is what? So rank is, if I get rid of this one, so I do, let me do the rank thing. So minus row 1 plus row 2, this will give me 1 1, minus 1 plus 1 is 0, minus 1, and this is 0 and 1. Then I do row 2 plus row 3. If I do that, I have 1 1, 0 minus 1. If I add these two, 0 0, and I can always do row 2 divided by minus 1, so this will be a plus 1. Okay, so I have two pivots, this pivot and I have this pivot. So if I have these two pivots, this implies, so rank is equal to 2, so this implies 2 independent columns. If I have 2 independent columns, this means what? This means A transpose A inverse exists. if A transpose A inverse exists, so what is A transpose A? So A transpose A is simply equal to, so the transpose of this one is 1 1 1 0 0 1, and this one is 1 1 0 1 0 1, which is equal to, so 1 plus 1 is 2, 1 here, symmetric matrix, 1 here, and then 1 plus 1, 2 over here. Okay. So what is A transpose A? So A transpose A whole inverse is simply, so what is the determinant here? So the determinant here is 4 minus 1, 4 minus 1, 3. So this is 3. So this is equal to 1 over 3, and I swapped these two. 2, 2 doesn't make a difference, minus 1, minus 1. And my pseudo inverse is simply A transpose A whole inverse into A transpose, which is equal to, and what is A transpose? So this is A transpose. When I multiply, I will get 2. So actually this is a 2 by 3 matrix. So 2 minus 1 is 1, so this is 1 over 3. Then I have 2, this is 2 over 3. Then I have minus 1, so minus 1 over 3. Then I have minus 1 plus 2, so it's 2 minus 1 is 1, so it's 1 over 3. Then I have minus 1 here, minus 1 over 3, and then I have 2 over 3, right? And if you compute, so an alternate method is you compute A plus equals, so instead of U sigma V transpose, we have V sigma plus U transpose. So since this is a tall matrix, so you should do compute eigenvectors of, so first step, compute eigenvalues and eigenvectors of A transpose A. So these will give you sigma square J, and this will give you Vj for J equals 1 and 2. 1, 2, because 2 is equal to R. Okay. So once you do that, then you compute columns of U for first R columns, use A into, so if it's a tall matrix, use A into Vi equals Ui into sigma I, right? Ui into sigma I for I equals 1 to R. And for R plus 1th column, so for I is equal to R plus 1 to M, you should do A transpose Ui equals 0, right? A transpose Ui equals 0. Let me see. It was in the last lecture. So when you have a tall matrix, A transpose Ui is equal to 0. Yeah. So this is how you'll find the columns of U. If you do that, then plug in the values here, where sigma plus is simply 2 by 3 matrix. So since your eigenvalues are, what were the eigenvalues? So let me calculate the eigenvalues. So eigenvalues over here is 2 minus lambda whole square minus 1 square equals 0. So this implies 2 minus lambda minus 1 equals 0, or 2 minus lambda plus 1 equals 0. So this is lambda 2, this is lambda 1 and this is lambda 2. So this is lambda 1, this is lambda 2. So this implies lambda 1 equals, no, this is lambda 1. Sorry. This is lambda 1, this is lambda 2. So lambda 2, so this implies lambda 2 equals 1, and this implies lambda 1 equals 3. So your sigma is going to be 1 over 3 under root, 1 over 3 under root, and this is going to be 2 by 3, so 0, 0, 1, and then 0, 0, right? And if you plug in these values from here and here, you'll get exactly the same answer as this one. So no need to compute the singular value decomposition unless somebody tells you to. Since the columns of A are independent, you can directly compute the pseudo inverse like this. Okay. And let's do another example. This one is A equals minus 1, 2, 2. This is the example, the first example that we did yesterday. This is actually equal to U. Over there, that was a column vector. Now we have a row vector. So U sigma V transpose equals, now U is actually 1. Sigma over there was a column. Now it's a row. So this was 3, 0, 0. So this is same example as in the last lecture. With the only difference that A is now a row vector, and not a column vector, is now a row vector and not a column vector. So if you do that, so this is U, this was V before, this is sigma. Instead of a column, it's a row, and then V is actually U, which was minus 1 over 3, 2 over 3, 2 over 3, 2 over 3, minus 1 over 3, 2 over 3, 2 over 3, 2 over 3, minus 1 over 3, right? Okay, and this is V transpose, and if you can compute your A, so this implies, and you can do that at home, I'm not going to do this for you, this is simply minus 1, 2, 2, 1 over 9. Okay. The last example is for a symmetric matrix. So 1, 1, 1, 1, and B is 0, 1. Okay. So obviously rank of A is 1. So we have only one independent column or row. So this equation AX equals B implies X plus Y equals 0 and X plus Y equals 1. So we want to find a solution for this one. So what is whether we do A transpose or A transpose is the same, because this is a symmetric matrix. So what is A transpose? So A transpose equals A transpose A. Why? Because A equals A transpose. So if I multiply with this one with itself, so 1 into 1 is 2, 1, 1, 2, 2, 2. So my eigenvalues are, so 2 minus lambda whole square minus 2 square. So this is equal to 2 minus lambda minus 2 equals 0. 2 minus lambda plus 2 equals 0. So this implies lambda 1 is equal to lambda 2, basically. This is lambda 2 equals 0, and this implies lambda 1 equals 4. Okay, so my sigma, so this implies sigma is actually 2000, right? It's like this, 2000. And what are my eigenvectors? So my eigenvectors are for u or v. So u or v, it's the same thing because the matrix is similar. So if lambda 1 equals 4, this implies a transpose minus lambda 1 I equals 2 minus 4 is minus 2. Sorry, 2 minus 4 is minus 2, 2, 2 minus 2. Or I can simply add these two. So this means row 1 plus row 2, I'll get 0, 0. And then I say row 2 divided by minus 2, so I get 1 and I get minus 1. So this is my pivot. So this implies u1, which is equal to v1, equals 1, 1, 1 by root 2. So this minus 1 comes here and is negative. Okay, good. And what about u2? And if lambda 2 equals 0, this is 0. Why? Because the rank is 1. It's less than the rank. Its matrix is not full rank. So obviously the determinant here is 0. So one of the eigenvalues has to be 0, and the determinant here is actually 0. 1 minus 1 is 0. So if lambda 2 is equal to 0, then A transpose minus lambda 2I equals this same matrix 2, 2, 2, 2, and I can do minus row 1 plus row 2, and then I do row 1 divided by, it's not row 2, it's row 1, sorry, it's row 1 divided by 2. If I do that, I have 1, 1, 0, 0. So this implies u2 equals v2 equals, so this is a pivot, so I have minus 1, 1, so this one goes here is negative, and this is 1 over root 2. So my u equals v equals 1 over root 2, 1 over root 2 minus 1 over root 2 plus 1 over root 2. Obviously, these are orthonormal and these are also orthogonal. These are normal, these are normalized to 1, and these are also orthogonal. Okay. And what you can do is, the pseudo inverse here is, so a pseudo inverse is, so A is U sigma V transpose. This implies A pseudo inverse is V sigma plus U transpose. And U transpose, okay. So V is 1 over root 2, 1 over root 2, minus 1 over root 2, 1 over root 2. This is V. Sigma plus is simply the inverse of this one. So it's 1 over 2, 0, 0, 1 over 2, 0, 0, 0. And so this is V. This is sigma plus. And then my U transpose is transpose of this one. So 1 over root 2 minus 1 over root 2, 1 over root 2, and 1 over root 2. And this is U transpose, right? And if you solve this one, you will get, if you solve this one, you will get 1, 4, 1, 4. You will get 1 by 4, 1 by 4, 1 by 4, 1 by 4. And x plus, which is a plus b, is simply, so b is 0 and 1, I think so. B is 0 and so I'm picking the second column. So if I pick the second column, this is simply 1 by 4. 1 by 4, or this implies, since this is x and y, so uh, uh, x by 4, so this simply means this is x, this is y, so x plus y is simply half. This is the least solution that you get if you use the pseudo inverse method. So the last proof that we want to do is, the last proof that we want to do before we end today's lecture is this one. So the proof is x, so claim is x plus equals a plus b, which we know is v here, sigma plus u transpose b, right? So, and we say this is the minimal length, this is the minimal length. So let me show is this is the minimal length. So the proof is like this. So we say multiplication by u transpose leaves lengths unchanged because u is a unitary matrix. This implies ax minus b equals u sigma v transpose x minus b, but instead of and b, let's say b here. Okay, so this is equal to sigma v transpose x minus u transpose b. Okay, so I multiply u transpose both sides. So this is, the length is not changed. So let's define. So let y equals v transpose x. So this is y. So, or this is equal to v inverse x, y, because v is orthogonal, and this has the same length as x. So v transpose x is x, y, because both these, and because v is orthogonal or unitary. So unitary, instead of transpose you use Hermitian. Okay, so this implies minimum of ax minus b is same as minimum of sigma y minus utb. Okay, so minimum of this one is same as minimum of this one. Also, now sigma is a diagonal matrix, and best y plus is, and what is the best y plus? This is, so y plus best is simply sigma plus, so from here, so y is best is sigma plus u transpose b, right? Or best x plus, and what is x plus? This is x plus is v times y. So v times y, so this is x plus is v times y plus v times y plus, which is equal to v times sigma plus u transpose b, right? Which is simply a pseudo p. And where v y transpose, even where is this one? V y transpose is in row space, and A transpose A X plus equals is A transpose B, where this is in row space, and this we know this is the normal equation from chapter 3. Normal equation from chapter 3. Okay, so before we end, if columns of A are independent, this implies A, which is equal to U sigma V transpose, and A transpose A, which is equal to V sigma transpose U transpose into U into sigma into V transpose. This is equal to I, and this is equal to V sigma transpose sigma V transpose. And we said okay, these were the eigenvectors, and A transpose A whole inverse into A transpose equals what? This is inverse of this one, so this is V sigma plus sigma V transpose, this whole transpose into A transpose, which is maybe I write it not here. It's going to interfere with my thing. This is, by the way, equal to V sigma transpose sigma transpose sigma into V transpose. Okay. Sigma transpose, this is not V sigma plus, this is sigma transpose sigma V transpose whole inverse into U sigma V transpose whole transpose. And when I expand this one, I'll get V sigma transpose sigma whole inverse into V transpose. Here I'll get sigma transpose here, and I'll get U transpose here. This, by the way, is identity. So what I'm left with is V, this is sigma inverse, this is sigma transpose inverse, this is sigma transpose, this is U transpose. Obviously, this is going to be identity, and I'm left with V sigma inverse into U transpose. V sigma inverse into U transpose, which, by the way, is a pseudo inverse. So this is n by n, this is n by m, this is n by m, this is m by m, and this is n by n. Okay, where sigma inverse is simply like this. This is a zero matrix, this is inverse here, this is a zero matrix, this is the inverse here. So this is all we wanted to talk about the applications of singular value decomposition, and hopefully you have liked this course and you have learned something from this course. I encourage you to understand the concepts and just don't solve the examples, or don't solve the question as you do in some other math courses. You need to understand what is meant by the spaces, what is orthogonality, what happens if you do not have a full set of eigenvector, what happens if you have eigenvalues that are zeros, what happens if the matrix is not square, can you still do decomposition, eigenvalue decomposition or not? To answer all these questions, you need to understand the material that has been presented to you. If you still have any questions, please email me those questions, either Dr. Babri or myself, or raise those questions when we are leading the discussions on Mondays and Wednesdays. Thank you very much for attending this course.